You think calm means safe. Look around you. The world seems stable. The sun rises every morning. The seasons cycle predictably. Your heart beats in a steady rhythm. The stock market, despite occasional bumps, trends upward over decades. Everything seems to follow patterns you can understand, predict, control, calm, stable, safe. It's a trap. The most dangerous thing you can do is mistake calm for understanding, mistake stability for permanence, mistake the absence of visible change for the absence of hidden forces building toward catastrophe. I spent my entire career studying systems that appear calm on the surface, but hide infinite complexity underneath. Systems where the peaceful center deceives you about the chaotic edges. Systems where everything looks stable right until the moment it isn't. And what I discovered changes everything you think you know about stability, chaos, and where the real action happens in nature and mathematics. Let me show you what I mean. Start with something simple. A pendulum. You push it. It swings back and forth. Regular. Predictable, the very definition of stable periodic motion. Scientists have studied pendulums for centuries. Newton used them. Galileo used them. They're the textbook example of orderly behavior. Now add a second pendulum, attach it to the end of the first one. A double pendulum, 2 arms, 2 pivots, same basic physics. Watch what happens. The motion becomes wild, unpredictable, chaotic in the technical sense. The double pendulum swings in patterns that never repeat. Tiny differences in starting position lead to completely different trajectories. You cannot predict where it will be 10 seconds from now, let alone 10 minutes. Same physics, same simple rules, but the system has crossed a threshold. It has moved from the calm interior of predictable behavior to the chaotic boundary where everything becomes sensitive and unpredictable. This is the first lesson. Calm is not a property of the universe. Calm is a property of where you're looking. The single pendulum seems calm because you're examining a simple system far from any threshold. Add one more degree of freedom, one more interaction, and suddenly you're at the edge. Suddenly calm dissolves into chaos. Now think about the Mandelbrot set, that famous fractal shape it spent years exploring. Inside the set, behavior is calm, iterations converge, numbers settle into stable patterns, periodic cycles, predictable outcomes. The interior is boring, mathematically speaking. Outside the set, behavior is also predictable in its way. Iterations explode to infinity. Numbers escape. The outcome is certain, just in the opposite direction, but the boundary, the edge between inside and outside, that's where everything interesting happens. That's where calm becomes chaos. That's where stability dissolves into infinite complexity. The boundary of the Mandelbrot set is not a line. It's a fractal dust of infinite intricacy. Points that stay bounded and points that escape are woven together so tightly that you can never separate them with finite precision. No matter how closely you look, you find more mixing, more complexity, more structure. This is not an accident. This is a fundamental truth about how systems behave. The center is calm because the center is far from any transition. The edge is chaotic because the edge is where different behaviors meet and compete. And here's the insight da necessität I restructure how you see the world. The interesting things, the important things, the things that determine how systems actually behave, they don't happen in the calm center. They happen at the chaotic edge. Let me make this concrete with examples from nature. Consider weather. Most of the time, weather is predictable enough. High pressure systems bring clear skies. Low pressure systems bring clouds and rain. The general patterns follow rules we understand, but sometimes weather becomes extreme. Hurricanes form, tornadoes touch down, heat waves persist for weeks, cold snaps, freeze everything. Where do these extreme events come from? They come from the boundaries, the fronts. The places where warm air meets cold air, where moist air meets dry air, where high pressure meets low pressure. The transitions, the edges. A hurricane forms when conditions are just right at the boundary between warm ocean water and cooler air above. The system is poised at a threshold. Small differences in temperature, humidity, and wind shear determine whether a hurricane forms or dissipates. The boundary region is exquisitely sensitive. The calm center of a high-pressure system is boring. Nothing much happens there, but the edges of that system, where it interacts with other air masses, that's where storms develop. That's where weather becomes interesting and dangerous. You can't understand weather by studying the calm centers. You have to understand the chaotic boundaries. Consider ecosystems. A mature forest seems stable. Trees grow slowly. Species populations fluctuate within ranges. The system persists for centuries. But look at the edges. The boundary between forest and grassland, the ecotone, as ecologists call it. That's where biodiversity peaks. That's where species from both ecosystems meet and interact. That's where new adaptations emerge. The interior of the forest is stable precisely because it's far from any transition. Everything has settled into equilibrium. But the edge is dynamic. The edge is where change happens. The edge is where the future of the ecosystem gets determined. When climate shifts, when conditions change, it's the edges that respond first. The boundaries move, the transitions relocate. The calm interior only changes after the edges have already transformed. Consider your own body. Your heart beats in a steady rhythm, calm, stable, predictable, but that's not quite true, is it? A perfectly regular heartbeat, one that never varies, is actually a sign of disease. Healthy hearts show variability, beat-to-beat fluctuations, subtle irregularities that indicate the heart is responsive and adaptable. Your heart is not operating in the calm center of its possible behaviors. It's operating near an edge, near enough to chaos that it can respond quickly to changing demands, near enough to stability that it doesn't collapse into arrhythmia. The healthiest state is not maximum stability. The healthiest state is poised at the boundary between order and chaos, ready to respond, capable of adaptation, not trapped in the rigidity of perfect calm. This pattern repeats everywhere I look. Financial markets. Most of the time, prices fluctuate within reasonable ranges. Volatility is contained. The system seems stable, but markets are not actually stable. They're poised at a critical threshold. They operate at the edge between orderly price discovery and chaotic panic. Most days, they stay on the orderly side, but the chaotic side is always there, always accessible, always threatening. When markets crash, they don't gradually become unstable. They flip suddenly from apparent calm to extreme chaos. The transition is abrupt because the system was never truly stable. It was always at the edge, always sensitive, always capable of catastrophic change. The calm you saw before the crash was an illusion. The system was operating in the boundary region where small perturbations could trigger large responses. The apparent stability was the trap. Tectonic plates. Most of the time, the ground beneath your feet seems perfectly stable, solid, reliable. You build cities on it. You assume it will always be there, but the plates are moving slowly, imperceptibly. They're grinding against each other. Stress is building. The system is accumulating energy that must eventually be released, and then suddenly an earthquake. The ground that seemed so stable lurches violently. Buildings collapse. The calm was always temporary. The stability was always an illusion, hiding the forces building toward catastrophe. The calm center of a tectonic plate, far from any fault line, really is stable. Nothing much happens there. But the boundaries between plates, the fault lines, the subduction zones, those are where the action is. Those are where the accumulated stress gets released in sudden, violent events. If you want to understand earthquakes, you don't study the calm centers of plates. You study the chaotic boundaries where plates interact. This brings me to the deepest insight from fractal geometry. The insight that changes how you should think about stability and chaos. Classical science loves equilibrium, systems at rest, forces balanced, steady states maintained indefinitely. Classical science treats departures from equilibrium as temporary disturbances that the system will correct, but most natural systems don't work that way. Most natural systems are not at equilibrium. They're driven systems, constantly receiving energy from outside, constantly dissipating energy, constantly operating far from any stable resting state. And driven systems don't settle into calm equilibrium. They settle into dynamic states at the edge of chaos. States where small perturbations sometimes die out and sometimes amplify. States where the system is maximally responsive, maximally adaptive, maximally alive. This is called self-organized criticality. Systems naturally evolve toward critical states, toward the boundary between order and chaos, because those states have special properties. Think about a sand pile. You drop grains of sand one at a time. The pile grows. At first, nothing much happens. Grains land, settle, stay put. But eventually, the pile reaches a critical slope. Now, when you drop a grain, it might trigger an avalanche, a small avalanche or a large one. You can't predict which. The system has organized itself to the critical state, to the boundary between stability and collapse. And here's the remarkable thing. The sand pile doesn't stay below the critical slope where everything is calm and predictable. It doesn't push above the critical slope where avalanches happen constantly. It organizes itself right to the edge, right to the boundary, right to the transition zone. This is what natural systems do. They evolve toward criticality. They find the edge between order and chaos, and they stay there, not because anyone designed them to, but because systems at criticality have maximum sensitivity, maximum responsiveness, maximum capacity for complex behavior. Your brain operates at criticality. Neural networks that are too ordered, too calm, can't process information flexibly. Neural networks that are too chaotic can't maintain stable representations. The brain finds the edge between these extremes and operates there. That's why you can think. That's why you can learn. That's why you can respond to novel situations. Your brain is not calm. Your brain is poised at the boundary of chaos, using that sensitivity to process information in ways that stable systems never could. Now, let me tell you why this matters for how you understand the world. When you see something that looks calm, you have two choices. You can assume the calm is real. You can assume the system is genuinely stable, that nothing dramatic will happen, that the future will resemble the past. Or you can ask, is this calm the interior of a stable region, or is it the apparent calm of a system poised at a critical threshold? The difference matters enormously. If the calm is real, if you're in the interior or secure of a stable region, then you can relax. Small perturbations will die out. The system will return to its steady state. The future is predictable. But if the calm is the boundary kind, if you're at a critical threshold, then the calm is deceiving you. Small perturbations might die out, or they might amplify catastrophically. The system might stay calm for years and then suddenly flip to completely different behavior. The future is radically uncertain. And here's the problem. These two kinds of calm look identical on the surface. You can't tell them apart by casual observation. You have to understand the structure of the system. You have to know whether you're in the interior or at the edge. Most people don't do this analysis. They see calm and assume stability. They see the absence of recent catastrophe and assume catastrophe is unlikely. They mistake the current state for the permanent state. This is the trap. Consider how people think about risk. They look at recent history. If nothing bad has happened lately, they assume nothing bad will happen soon. They extrapolate from the calm center of their experience to the chaotic boundaries of possibility. But many systems are not well described by their calm behavior. Many systems spend most of their time in relatively stable states, but occasionally flip to extreme states. The extreme states are rare but enormously consequential. They dominate the long-term behavior, even though they're absent from short-term observation. Financial markets do this, earthquakes do this, pandemics do dynamische situaties, extinctions do political revolutions do this. If you only look at the calm periods, you miss the most important features of the system. You miss the boundaries, you miss the thresholds, you miss the potential for sudden catastrophic change, the geometry of roughness, the mathematics of fractals teaches you to look differently. It teaches you that complexity lives at the boundaries, that the interesting behavior happens at the edges, that smooth, calm surfaces often hide rough, chaotic structures underneath. When I look at a system, I don't ask whether it's currently calm. I ask where the boundaries are, where are the thresholds, where are the transition zones, what would happen if the system moved from the interior to the edge. This is fractal thinking. This is the perspective that decades of studying rough, irregular, complex structures has taught me. The world is not smooth. The world is rough. The world is not stable. The world is poised at countless critical thresholds. So the world is not calm. The world is filled with boundaries between different behaviors, boundaries that can shift suddenly and catastrophically. Classical thinking sees a stable system occasionally perturbed by external shocks. Fractal thinking sees a critical system constantly generating its own complexity, constantly evolving at the edge of chaos, constantly capable of sudden transformation. The fractal perspective is not pessimistic. It's not about expecting disaster everywhere. It's about understanding where you are in the structure of possible behaviors. It's about knowing whether the calm you see is robust or fragile. It's about being prepared for the boundaries even when you're experiencing the interior. Let me close with what this means for how you should see reality. When you look at a coastline, you're not seeing a simple boundary between land and sea. You're seeing a fractal structure with complexity at every scale. The apparent simplicity is an artifact of your viewing distance. Zoom in and the complexity reveals itself. When you look at a cloud, you're not seeing a simple white puff. You're seeing the visible signature of turbulent processes, chaotic mixing, boundary effects in the atmosphere. The calm appearance hides dynamic complexity. When you look at any system that seems stable, ask yourself, where are the boundaries? Where are the transition zones? What would push this system from the calm interior to the chaotic edge? Because the boundaries are always there. The thresholds are always there. The potential for sudden change is always there. The calm you see might be real, or it might be the most dangerous illusion of all. Stability is not the natural state of the universe. Criticality is. Systems evolve toward edges, toward boundaries, toward the transition zones where complexity maximizes and prediction fails. The calm center is the exception. The chaotic boundary is the rule, and the boundary determines everything important about how the system will behave. This is what fractal geometry teaches. This is what the mathematics of roughness reveals. This is why I spent my life studying the irregular, the complex, the rough, because the smooth surfaces are not where the action is. The calm interiors are not where the future gets determined. The stable equilibria are not where nature actually lives. Nature lives at the edge. Nature lives at the boundary. Nature lives in the transition zones where order meets chaos and complexity emerges. Calm is a trap because it makes you think you understand. It makes you think you're safe. It makes you think the future will resemble the past. But if you're at a boundary, if you're near a threshold, if you're poised at the edge of chaos, then the calm is lying to you. The stability is temporary. The safety is an illusion. The only way to avoid the trap is to understand where you are. Interior or edge, robust stability or critical threshold, real calm or the dangerous quiet before the storm. Fractal geometry gives you the tools to ask these questions. The mathematics of roughness gives you the language to describe what you find. The science of complexity gives you the concepts to understand why boundaries matter more than centers. The world is rough. The world is critical. The world is poised at edges. And knowing that, seeing that, understanding that is the beginning of real knowledge, not the comfortable knowledge of smooth approximations, not the false confidence of assumed stability, but the true knowledge of how complex systems actually behave. The boundary never stops generating complexity. The edge never stops producing surprises. The transition zones never stop mattering more than the calm centers. That's the truth fractal geometry reveals. That's why calm is a trap. That's why the most important features of reality live at the boundaries, not the interiors, not comfort, not stability. Truth